Hi, welcome to my presentation, Secure Data Processing at Scale. Many of today's companies are data companies, and at their very core of their businesses lies sensitive data, such as medical records, financial data, or other classified information. And on the other sides, there are companies that operate on sensitive computations. These are secrets or tools developed by the companies, such as artificial intelligence, machine learning pipelines, or algorithms that define their businesses. What these two types of companies have in common is the fact that they need a massive, secure IT infrastructure to process these assets. And by assets, I mean both sensitive data and sensitive computations. The need for this secure infrastructure has become universal and made secure data processing a hot topic in industry and academia. For scalable data processing, cloud has become a de facto standard. Typically, both small startups and large corporations do not own any infrastructure, but rather outsource it to public cloud providers. Take as an example Netflix, Airbnb, or Lyft. These companies almost entirely move their operations to public cloud. But companies that operate on sensitive data and computations cannot benefit from this technology. The nature of their assets require full confidentiality and privacy, which in today's public cloud is not guaranteed. The technology itself creates the possibility for cloud providers to access the data. Sometimes, even the national law may require the companies to expose some of it to the government agencies. This is an absolute no-go for many companies operating on sensitive assets. As of today, they cannot benefit from this technology at all. The result is that they're building their own infrastructure because they can't trust anyone, because none of the public cloud providers can technically prove that neither they nor any authorities have not accessed their data nor spoofed on their computations. And working on on their own premises, they sacrifice scalability and efficiency. A good example of it is the healthcare domain, where most applications use in-house infrastructure. This is not a new problem, and it has been already recognized by the community, which as a solution proposed a hybrid cloud. The idea behind hybrid cloud is that you split your data between sensitive and insensitive data, and then whatever is tagged as insensitive, you send for processing in the public cloud, while whatever is tagged as sensitive stays in the private part. But we're talking about companies that have sensitive assets at their core, assets that define their businesses, so the vast majority, if not all of their assets, will be sensitive. So when trying to run on hybrid cloud, they still end up with the need mostly for private infrastructure. What is still missing in the public cloud is some sort of privacy protection that can be guaranteed and controlled from the private cloud. Had we had that, we could trust the public cloud as much as we trust the private, and we could safely delegate data and computations. There are few systems that work on encrypted data, but most cloud-based data processing systems, such as Flink or Spark, still expose data and computations on the hardware level. In the recent years, a kind of protection we were looking for started offering trusted execution environments. The so-called TEEs can guarantee full protection and confidentiality on remote machines. Intel implemented this technology and called it Intel Software Guard Extension, or simply Intel SGX. In this thesis, we envision a system that enables to move sensitive assets to the public cloud as much as needed, and to secure these public domains using trusted execution environments. It has already been shown in many works that these environments can provide security, but come at a high computational cost. So the biggest challenge of this thesis is how to enable efficient data processing jobs to hybrid compute environments. But first, let's take a step back and understand how trusted execution environments work. In a regular processor setup, the CPU takes two inputs, code and data. Inside of it, it executes the code on the data and then writes out the results of it again as data. It also works closely with the main memory, where it can store its inputs and outputs. In Intel SGX, this setup was redesigned. Inside of the CPU, we are now able to create secure enclaves. You can think of them as a type of secure containers. They are unaddressable, encrypted, and completely isolated from any other processes. Inside of them, they store a cryptographic key that also cannot be seen by anyone else. It allows them to receive code and data in encrypted form, decrypt it inside of the enclave, execute, and again encrypt the output. These inputs and outputs are now stored in a special area of the main memory called Enclave Page Cache, or EPC. It is an encrypted and integrity-protected memory area that is maintained and used by the secure enclaves. As you can see, from now on, anything that SGX operates on is in an encrypted form. A potentially malicious administrator that would snapshot the memory or read the buses would only see encrypted garbage. Of course, nothing comes for free. The classic insecure CPUs can be very fast and can operate on very large memory, while Intel SGX is completely the opposite. It is slow, it runs on very small memory, but it is considered secure. This creates many challenges when building systems. First, it's the memory. Intel SGX operates primarily on the EPC part of the main memory. After allocating space for the metadata, it leaves only around 90 megabytes for user application and data. It is technically possible to go over those 90 megabytes, but it triggers an extremely costly paging. This is highly discouraged by Intel and by authors of many SGX publications. Second is a very expensive CPU instruction set. Things that we have been doing for years and they have been fast now require many security checks which slow down anything we do. And lastly, the communication with the enclave from the outside world is minimal. This implies no system calls which are considered insecure. It requires a new and completely different way of designing systems. We have tried to measure just how expensive it is to execute code on Intel SGX. And this graph shows the results of our experiments. We created linked lists of different sizes, both in native applications and in an SGX enclave. We accessed these lists sequentially and randomly and compared SGX execution to native execution. On the x-axis of the graph is the size of the linked list. On the y-axis, it's the normalized runtime with regards to native. The sequential read is the red line. We can see that until the list size reaches the L3 cache size, the CPU does a great job prefetching data. The results are comparable with the native. Until the EPC size, the results get worse and worse because now the CPU has to also access the EPC and not only the caches. Once the size of the list crosses the EPC size, it stabilizes on a level 1 order of magnitude worse than the native. Well, if that would be the price for security, not bad at all. But if we take a more real-life example and read the list randomly, we can see that crossing each cache level size, we get enormous performance degradation that for a list larger than the EPC size reaches 3 orders of magnitudes and doesn't stop growing. It is pretty clear why crossing CPU cache levels causes some performance reduction. The caches have to be filled with the new data and creates a bottleneck. But the immense rise when crossing the EPC size has another origin. It is caused by the way how Intel SGX handles paging data out of the EPC. So once SGX runs out of space in the EPC, it can keep allocating memory only if it pages out some of its content to unprotected areas of the main memory. This is a very costly process that includes multiple encryption and encryption of the data both by the CPU and the on-die memory controller. It creates a new bottleneck that significantly slows down the execution of the entire program. It has been estimated that an EPC hit takes 200 CPU cycles, while an EPC miss, 40,000 cycles. This is one of the places where we will investigate where the cycles are used by the CPU. Can we reduce the costs and new ways of processing data that avoids this highly costly process? So after that, we wanted to find out how it is translated to real performance. And to figure it out, we ran an experiment that compared a simple no partitioning hash join algorithm on native CPU and using Intel SGX. We implemented the algorithm in C and translated it for SGX. We ran the experiment on the same machine and on the same dataset. We can see that the native version reached a throughput of a little bit over 3 million tuples per second. Its SGX translation reached only 50,000 tuples per second. This is a difference of 2 orders of magnitude, and this is one of the biggest questions in this thesis: how to significantly reduce the gap between native and SGX execution. That is, how to improve the SGX performance and get as close as possible to the native throughput. This will be our main focus in the next months, to investigate new ways of improving relational operators running on Intel SGX. Well, this is our target for the next steps, while our long-term goal is a vision of a distributed system that efficiently executes relational operators in hybrid cloud. And here we can see its architecture. It comprises a main node and compute nodes. The main node receives a query from the user and does the regular steps of parsing, optimization, and compilation. It then delegates the execution to compute nodes, which can be either private or public. And private compute nodes are considered secure and run as a classic compute node of any known distributed system, while public compute nodes are running in insecure environments and need to be protected with trusted execution environments. All the communication and data must be kept encrypted, which is shown in the graph with red arrows. The public nodes can communicate between each other in plain text, and this is shown as green arrows. You can find more details about the system in the paper. To summarize the talk, we have shown that many companies that work on sensitive data and sensitive computation can't use cloud as it is. Hybrid cloud tried to mitigate the problem, but for many, it didn't solve it. Technologies like Intel SGX are offering a possible solution, but it's still not clear how it can be used to improve the status quo. There is a lot of confusion and uncertainty how it works specifically at the lowest levels and how it behaves in different scenarios. Our next steps will be to understand in details how the data is processed on SGX and how it can be exploited for building data processing systems. We'll then start experimental evaluation of relational operators on SGX to see how joins, group bys, and aggregations behave. With this knowledge, we will propose new implementations crafted for secure environments. These are the references for the sources used in the presentation, and I'm ready to take questions.